Hello CFA friends. In this quantitative methods reading we will look at the topic of multiple regression, and we'll finish off also looking at some issues in general relating to regression analysis. So quite a lot to cover in this particular reading, so let's get started. So firstly we want to look at what a multiple regression line looks like. And of course, we are still trying to explain our dependent variable, but this time we expand the analysis by saying that this dependent variable doesn't only depend on one explanatory variable, i.e. x1, but it may also depend on other things as well. In a minute we'll see a concrete example, a real research that was performed to cover us for multiple regression. But again, we've got an intercept, we've got slopes, as many slopes as independent variables, so these are partial slope coefficients, or you can think of them as sensitivities or exposures to the risk factors that we have identified in our regression. And of course we finish off at the end with our good old usual suspect, which is the error term, or the epsilon, the unexplained noise element of our regression. So here's a concrete example. This is in fact a study performed by two hedge fund researchers, Fung and Xie, in 2002, whereby they regressed hedge fund returns, which is our dependent variable, against three independent variables. And you may remember that our notation for number of independent variable is k, so k is equal to 3. So the three independent variables here are small cap stocks, high yield bonds and emerging markets. Essentially the logic Fung and Xie took for this particular regression was the idea that hedge funds are potentially risky investments, so engaging risky investments or strategies, so we can explain them with risky asset classes such as small caps, junk bonds, emerging markets are also risky. And so this is what the regression looked like. Now specifically for small cap stocks they use the Wilshire 70/50. For high yield bonds they use the Credit Suisse First Boston High Yield Bond Index, and for emerging markets they use the emerging market index called IFC. Please note that this is simply for illustration purposes, so we are not going to be asking you to memorize the facts of this particular study. So they regress hedge fund returns against our independent variables for a period between Jan 94 to September 2001, which turns out to be 93 monthly observations, so that's our sample size equals 93n. And of course we have three independent variables, so k is equal to 3. So we do keep track of these n's and k's as we go along, because of course they kick in various computations, ANOVA tables, etc., etc. So of course we first have to perform a hypothesis test to identify which sensitivities or which slopes are significant. And you may remember that the typical case is that of the statistical significance case, i.e. is the slope actually different from 0. Now hypothesis is the one researcher wants to reject, so slope is equal to 0. We want to reject that, and of course if we do, we will find that our slope is either positive or negative, but certainly not 0, and therefore it has some statistical significance. This is a t-test, and it comes with its own degrees of freedom, which are n minus k minus 1. In multiple regression, it's very important to keep these degrees of freedom generic, because whilst simple linear regression degrees of freedom were always n minus 2, here the k is variable. There will be some regressions with 2 independents, 3, 4 or more. Therefore, it is the best idea to keep it generic, n minus k minus 1. The actual computed t-statistic is exactly what we saw in simple linear regression, and essentially it's the estimated slope minus the hypothesized slope over the standard error of that slope. But because the hypothesized slope here is in fact 0, the formula simplifies into estimated slope over standard error. Now, of course, one way to test, maybe before I even talk about p-values, just to reiterate that we will reject the null hypothesis, reject null if the absolute value of the computed stat exceeds the absolute value of the critical stat, in this case the critical t-stat. This is one way to reject the null. A second way to reject the null is using p-values. Now, p-values are probability values under a curve. In fact, what a p-value is specifically, if I have a distribution, and just for the sake of argument, it will be alpha 5, 1 tail, right, just for simplicity. So this area here, which is our significance, will be equal to 5%. Now, what is the p-value? The p-value is the probability to the right of the computed value. So if this is my computed value, the probability to the right of the computed value is my p-value. Okay, so essentially in this case, in this picture, we've got the critical value. To the right of the critical value, by definition, in a one-tailed test, we've got 5% significance. To the right of the computed value, we've got the p-value, the probability to the right of the computed value. So notice that based on computed and critical values, you will quickly observe that we are in the rejection tail, and therefore we have to reject the null hypothesis. But we can do the same based on the p-values. We can say that we want to reject the null if my p-value is less than my significance value. Because the only way p-value will be less than significance is if the computed value is greater than the critical value. So these two ways of rejecting the null are pretty much redundant. They're doing the same thing, so they will never conflict. P-values are provided by packages that we provided also on exam day, so literally everything you got to do at that stage is pick the p-value, look at it, compare it to the alpha. If it's lower than the alpha, you can reject the null hypothesis. And of course, a question I get asked often is what happens if the test is not a one-tailed test, but it is a two-tailed test. Do I have to divide the p-value? Do I have to multiply the p-value? And the good news, guys, is that you don't have to do anything to it. The computer automatically adjusts the p-value if the test is a two-tailed test. So you literally have to only focus on comparing the p-value to the value of significance. So here's an example of that. Say we are performing a base case test of significance 5, which of course corresponds to a confidence level of 95, and we then know that our p-value for that particular test is 7%. Well, because we notice that 7% is greater than 5%, we therefore fail to reject a null because the p-value is greater than alpha. Also, whilst correct, this statement is probably of lesser significance to us, but p-values can be viewed as the smallest significance level at which we can reject the null hypothesis. I think that by far is the more useful way to remember p-values, however. Okay, so going back to our Fung and Xie example of hedge funds, they've got the intercept, they've got Wilshire, which is small caps, So that's our B1. High yield bonds is our B2, and IFC is our emerging markets. So that is our B3. So the first column simply gives us the values of the intercept and the three slopes. The second column gives us the appropriate standard errors for each of them. The third column gives us the t values, computed t values. We have blanked out one of them so that we can compute it together and see how that works. And the fourth column gives us the computed p values, which of course can be used instead of t values. Now, how do we interpret the coefficients? So we saw that the intercept was equal to spot 008, and that will be the return of hedge funds if all three independent variables are flatline, if their return is equal to 0. So you can think of the intercept as the alpha in hedge funds, the return hedge funds will have that is not explained by the three independent variables. So maybe abnormal return not explained by the three independent variables. Now, in terms of the actual slopes, the way we interpret them is kind of similar to the way we would interpret a slope in simple linear regression. But of course, because there are more than one slopes, we have to add one very important piece of wording. And that is that we are keeping everything else the same. So in other words, because the Wilshire slope, the small cap slope, was 0.278%, we can say that for 1% change in the return of the small cap index, hedge fund returns will move by 0.278%, holding everything else the same, holding higher bonds and holding emerging markets constant. So these are indeed partial slope coefficients or partial sensitivities, holding everything else the same. Also, another thing we may want to notice here is that hedge fund returns are not going to be influenced by high yield bonds. There were two ways to discover that. If I go back to the actual table and I focus on high yield bonds, the first thing that I can notice, and that's a quick one, the p-value is huge. Indeed, it is higher than our significance of 5%. Right? Our significance is 5%. Our p-value is much higher than that, so high yield bonds are not significant. i.e., this value is not statistically significantly different from 0. Second way, of course, is to look at the t-stats. Look at this. The t-stat is 1.4. Now, some may say, now we have to go and look up a t-table and find the critical value. But that is not necessarily the case. You should be vaguely familiar with some bread and butter critical values. So, for example, if alpha is 5, if your significance is 5%, okay, and because we're looking at statistical significance, we have two tails. So if we've got two tails, and also if we've got a large sample, that means that my critical t value is approximately equal to the magic number 2. Now, you may kind of explain this to yourselves by saying that as sample sizes get larger, as degrees of freedom increase, t-tables converge to the z-tables, to the normal distribution. And of course, the critical value from the normal distribution for alpha equals 5, two tails large sample, would have been, any guesses? 196. Approximately 2. Approximately 2. So that's what we are talking about. Because 1.4 does not exceed 2, we will fail to reject the null hypothesis that the slope on high yield bonds is equal to 0. We fail to reject that, and therefore we discover high yield bonds are not statistically significant. Risk factor. Okay, now we're going to look at confidence intervals again. So from simple linear regression, nothing's really changing here. We still have this equation holding. We take the slope estimate, the b hat, plus or minus critical t-stat times the standard error of the slope. Remember, the critical t-stat will depend on the significance of the test, 1 minus confidence, and the degrees of freedom n minus k minus 1. Remember to keep those degrees of freedom generic here and not to fall into the trap of using n minus 2 for multiple regression. K is variable and you have to keep it that way. Also confidence intervals, because we go both ways around the estimated slope, are going to be a two-tailed situation. Now, okay, obviously the point behind coming up with this relationship is to actually predict the dependent variable ultimately. So if Fung and Xie now think that small caps are going to rise by 10%, high yield bonds will go up 3%, but emerging markets will plunge, then essentially what that means is that we can plug the data in our bread and butter equation. Here's the B0, the intercept. Here's the B1, the exposure to emerging, the exposure to small cap stock. So that is your Wilshire estimate. The B2 is the exposure to high yield bonds. There you go. We predict higher bonds will rise. And B3 was the exposure to emerging markets. And our estimate of IFC is -2. So given all these predictions, we can then say that we expect the monthly return of hedge funds in the coming month to be 3.7%. Of course, notice that in this equation, we do not add an epsilon, because when we predict, of course, we expect the value, the expected value of this epsilon to be 0. Now, exposed after the fact, once the hedge fund returns are actually out and available, we will take the difference between the actual return, what actually happened, and what we thought was going to happen, 3.7, and that'll be the realized epsilon from the regression, the realized error or residual. Okay, so assumptions of multiple regression. Well, guess what? A lot of them are going to be the same as simple linear regression. We're still talking about a linear relationship between the two variables, or between the y and the x's. We're still saying that the expected value of epsilon has to be 0. Some epsilons are above the line, some are below the line, but they overall offset. Variance of error term is constant, so that was the idea of Heteroskedasticity or Heteroskedastic error term. That is a key assumption, and if we violate it, we'll be looking at Heteroskedasticity, which is coming up. Error terms are not serially correlated. Of course, if we violate that, we'll get serial correlation, autocorrelation, i.e. a situation where the value of the error term today drives the value of the error term in the next period. And finally, we've got error terms are normally distributed and well behaved. So no surprise there. Now, the only new point on top of simple linear regression is this point. Right. We don't have an exact linear relation on the axis. So if I had, for example, two x variables which were perfectly correlated, for example, I made a mistake and I included the same variable twice, that will be a case of perfect multi-collinearity, and that will be just a mistake in my regression, and it won't work. So including the same variable twice would be certainly a big problem. But also having variables that are highly but not perfectly correlated is still a problem. This problem is referred to as imperfect multi-collinearity and occurs when we've got two or more variables that are highly correlated. So we would want to try and avoid that problem. So for example, if I had interest rates and inflation at the same time in my model, one could go up when at the same time the other one goes down, and that could potentially lead to various problems we shall see later. Now, we also have a more generic test on top of your t-tests. So your t-tests were basically pointing the finger at various slopes and saying, okay, how about small cap stocks? Is that a significant variable? How about emerging markets? Is that a significant variable? How about high-yield bonds? Is that a significant variable? So t-statistics look at individual significances of the variables. The f-test is a test of the overall validity of your model. So this one is a binary kind of test. It says, yes, the model works, no, the model doesn't work. So overall validity. Now, the key point is that it actually tests whether any of the independent variables help explain the dependent variables. So it doesn't necessarily say, yes, all variables are doing a brilliant job. Well done, guys. You selected the best variables in the world. It says that at least one of the slopes is doing a good job. Okay, but let's start with the now. The now is, of course, the gloomy worst-case dim scenario that B1 is equal to B2 is equal to B3, which is equal in turn to 0. So in other words, this is the worst-case scenario where you basically selected 3 or more or less, certainly more than 1. All independent variables are unrelated to the dependent variable. That's a worst-case scenario. So if we were able to reject that worst-case scenario, we end up concluding that at least one, perhaps the B1 or the B2 or the B3 or maybe 2 or maybe 3, but more than 0 independent variables are significant. At least one is different from 0. Now this kind of test is a one-tailed test. Now why is it a one-tailed test? See, if I actually imagine my F distribution, right, non-normal distribution, bounded by 0, okay, F is a distribution that is a ratio of squared numbers, so it cannot be negative. We basically only have one tail to the right. So maybe I have my 5% here, 5% here. And essentially what this test is saying is that if you don't reject, if you stay in the main body of the distribution, the answer to your question is no, the model does not work. So you fail to reject the null hypothesis, jointly the 3 slopes are equal to 0. But if you're in the right tail, then the answer to your question is yes, the model does have some validity because at least one of the slopes is going to be different from 0. So the mechanics of the test, thankfully, are exactly the same as the mechanics of the t-test. We reject the null if the computed F value exceeds the critical F value from the table. Now, of course, the mechanics of the F table are slightly different to the mechanics of the t-table because we've got 2 sets of degrees of freedom. One for the numerator of the computed formula and one for the denominator. It will become more obvious as we actually see the formula itself. So this is the formula for our computed F. Okay, so in the numerator we get the regression sum of squares divided by the number of independents. So think of this, the numerator is essentially the explained variation per independent variable, and that's also known as mean squared regression. In the denominator, we've got the sum of squared errors divided by its degrees of freedom. So essentially, we're looking at the amount of unexplained variation. So in a nutshell, what this is saying, what the computed F is saying, is give me the ratio of the average explained over average unexplained variation. Well, the F value will be high if we've got a lot of average explained variation per unit of unexplained variation. And that's, of course, when our models will tend to work. So we want high F values. They're going to be indicative of powerful models where at least one, possibly more of the independents help explain the movement in the dependent variable. Now, of course, in this formula, we've got a numerator and we've got a denominator. So the numerator has its own degrees of freedom, which equal to k, i.e. the number of independent variables. The denominator has its own degrees of freedom, which are equal to n minus the number of independent variables, minus 1. And those two sets of degrees of freedom is what we need for looking up our F table. So how does that work? Suppose this is our F table. You can find such table at the back of your Schweizer books. Hopefully, such a table is provided also on exam day. Now, because for the Fung and Xie example, we know that k is 3, we go 1, 2, 3 to the right along the first row of this table. And then, because we know that n minus k minus 1 will be 93 monthly observations minus 3 independent variables minus 1, this will give me 89 degrees of freedom. I go 89 levels down along the first column, and that will show me the critical value. Do remember that when looking up this F table for a 5% significance, you need to be using the 5% F table and not the 2.5% F table, because remember, this type of F test has to be a one-tailed test. So the entire 5% is in the right tail. So once you've got that, if this is your critical value, you go back to your formula for the computed F, and if the computed F is indeed higher than 2.7, you can reject the null and conclude that overall your model has some value. Now, moving on to our good old coefficient of determination. Remember, we call this the R squared of the regression. So in multiple regression, it still means pretty much the same thing as in simple. An R squared of 0.876 would mean that 87.6% of the variation in Y is explained by X. The only new thing here is, of course, we've got more than one X. So which X exactly explains 87.6? Unfortunately, R squared does not split the explanatory power across the independent variables. What it basically tells you is that collectively, together, the three independent variables, which were the small cap stocks, high yield bonds, and emerging markets, help explain 87.6% of the variation in hedge funds. But it doesn't split it across the independents. So if you actually wanted to focus on each one separately and try and understand whether it's doing a good job, guess what? You're back to the world of individual t-tests and t-statistics. Now, R squared on its own will not do a perfect job. And I think this picture shows you this beautifully. Now, essentially, as we increase the number of independent variables, as we increase k, the unadjusted R squared always goes north, always increases. And you might think, well, that's brilliant. So we managed to explain more of the variation in Y. But the problem here, guys, is that you could be adding completely unrelated independent variables. As I say, you could be adding snowfall in the French Alps, right? And even if you added that to the Fung and Xie example, the R squared on the hedge fund returns will go up. Although we probably know there's no relation, there's no economic reason why snowfall will drive hedge fund returns. Okay, so there's a mathematical deficiency problem when it comes to R squared, unadjusted R squared. It simply, quite simply, increases regardless of the quality of the new variable. That is why we also like to compute something called adjusted R squared, which is effectively better penalizes for the introduction of new independent variables. What essentially does is it introduces a penalty factor. And here's your equation for adjusted R squared. Now, again, I wouldn't be spending sleepless nights trying to memorize the equation before I can actually understand what the equation is doing. What the equation is doing is it's taking the unadjusted R squared. Now, this unadjusted R squared will go up as I add new independent variables. So, if k goes up, there is no doubt about it, R squared will go up. So, this R squared will go up regardless of the quality of the added variables. But here comes the trick. The adjusted R squared applies the penalty factor in the form of k here in the denominator. So as R squared goes up, k goes up as well. So in that case, adjusted R squared may go up if the new variable is powerful enough to cause an adjusted R squared to increase significantly. But an adjusted R squared may also go down if the new added variable is doing a poor job. So you can see a couple of mathematical facts relating to adjusted R squared in this picture. First mathematical fact is that adjusted R squared is mathematically always lower than R squared. In fact, our R squared for this regression is 87.6, but our adjusted R squared is 87.2. The second mathematical fact is that adjusted square may go up as well as down, whereas unadjusted R squared can only go up as we add new independent variables. So what typically happens is adjusted R squared tends to go up as we add new variables, as we improve, genuinely improve the explanatory power of our model. But there comes a point where diminishing returns will kick in. This is the point where researchers start to overfit their models. You may have come across an expression called data mining, right? So you don't want to data mine your models, you don't want to overfit your models. Because if you keep adding independent variables in an attempt to better explain the world, eventually you'll destroy value and your R squared will decline, potentially even turning into negative territory. So fact number 3 about adjusted R squared is that adjusted R squared can be a negative number. Remember, unadjusted R squared cannot possibly be less than 0, because unadjusted R squared is nothing but RSS over SST, which is a ratio of essentially 2 positive squared numbers. Right, now interpreting adjusted R squared. So suppose our friends Fung and Xie here get overexcited and add 15 more independent variables. So our k is now the original 3 independent variables plus 15 equals 18. So possibly a good candidate for an overfitted model, a data mined model. Now, as we agreed, due to the mathematical properties of R squared, this will actually go up to 89. Okay, it might go up to another number, but in this case to 89 from the original of 87.6. So if Fung and Xie don't know the story about adjusted R squared, at this point they might think, oh, this new model k equals 18 is actually doing a pretty good job. Must have hit, the gold mine here, and we found more explanatory variables, so the model's doing a better job. Of course, the problem is it's not necessarily because you added the new quality variables, it's simply because you increase the number of independents. That's why R squared's going up. Really what we should be focusing on is our adjusted R squared. And our adjusted R squared, of course, will apply the famous penalty factor in the form of the number of independent variables in the denominator. And what we'll discover now is that our adjusted R squared has declined from the original value of 87.2. So what should be my ultimate conclusion, and which model, more importantly, should I choose at this point? And of course, you want to be efficient. So choose the model with the highest adjusted R squared. And this is essentially your original model. You were explaining the world better with only 3 variables, and you're now explaining the world less well with 18. So the original model is essentially more efficient. Stick with it. Okay, changing direction altogether, we're now going in the world of dummy variables. These are also known as qualitative independence, qualitative axis, or binary axis. Now, why are they called binary or qualitative? Well, because they can only take 2 possible values, 0 and 1, or if you prefer, yes and no. Right. So what could be one application of this sort of variable? Well, suppose I had a regression where one of the variables I wanted was whether the company defaulted or survived. So default could come with a dummy value of 1, and survival could come with a dummy value of 0. That's one application. But the one that we're going to look at today is the application when it comes to calendar studies. So suppose you were interested to see whether you could make some abnormal money by trading intra-week, or depending on maybe month of the year, or day of the month, etc., etc. So any calendar study that essentially attempts to make money by trading the calendar. So in our example, we will regress earnings per share against binary variables that account for quarter. You could, of course, come up with dummy variables for days of the week or months of the year. We'll just do a quarterly study. Now, remember with dummy variables, however, that you are trying to avoid, as much as possible, falling into the famous dummy variable trap. Now, logically, one might say there are 12 months in a year, so I gotta use 12 dummies. There are 4 quarters in a year, so I gotta use 4 dummies, right, for the quarterly study. This is adamantly wrong, because if you use 4 dummies for 4 quarters, you fall into the trap of perfect multicollinearity. If you use 12 dummies for 12 months, you fall in the trap of perfect multicollinearity. Always use 1 less dummy than states of the world. I.e., for our quarterly study, we'll be using 3 dummies for the 4 quarters. Which, of course, will be begging another question. What happens to the omitted dummy? And we'll see that in a minute. Now, so here's our regression. So we've got the earnings per share at different point in time. That's given by intercept, and then the first 3 quarters are represented by 3 dummy variables. So Q1 is the dummy variable for the first quarter. And of course, you can think of these dummy variables as light switches. They can either take the value of 1 or the value of 0. So, for example, if my earnings per share were generated in the first quarter, I'll set this dummy to 1, but these 2 dummies to 0. Right? If my earnings per share were generated in the second quarter, then this will be 0, this will be 1, and this will be 0. And finally, I'm sure you're getting the pattern. If earnings per share coming from the third quarter, I'll have 0, 0, and 1. The point being that you can never have more than 1 dummy set to 1. Right? Because you can never be in 2 places at the same time, unless you clone yourself. Now, basically what we're going to do here is we're going to also think about what happened to the fourth quarter. So, fourth quarter, by definition, this will have to be 0, because we're not in the first quarter. This will have to be 0, and this will have to be 0, right? Now, if we're in the fourth quarter, essentially the only thing that remains in this regression is the intercept. So, by definition, we can make a big statement here. the intercept is equal to the omitted dummy. The intercept is equal to the omitted dummy. Right? So let's see now concretely with numbers in this regression what happens. So let's say this is what we've got. The B0, the intercept is 125, B1, B2, B3. Okay, we're going to ask ourselves a couple of pretty much qualitative questions because no computation, no big computation will be required from us here. What is the mean fourth quarter earnings per share? Well, we know that the omitted quarter is the fourth quarter. We know that the fourth quarter is represented by the intercept, so that's a quick answer. The earnings per share in the fourth quarter have to be $1.25. Here's another question. What is the predicted first quarter earnings per share? Okay, nothing easier than that. In the first quarter, or actually let's do it here, in the first quarter, EPS 1 will be equal to intercept of 125, that's like a constant that never changes, plus spot 75 times, because we're in the first quarter, we set that to 1, we set everything else to 0, so the result is $2. So that's the answer for the first quarter. So if you think about it, it's all actually measured relative to the reference point, which is the fourth quarter. So this number is your reference point. You know your earnings in the fourth quarter is 125. So basically what you could think of is this slope for the first quarter basically tells me how earnings per share in the first quarter relate to earnings per share in the fourth quarter. So the statement I can make is that in the first quarter, earnings per share are 75 cents greater than the fourth quarter. Similarly, I could say earnings per share in the second quarter are 20 cents less than earnings per share in the fourth quarter. And finally, earnings per share in the third quarter are 10 cents greater than earnings per share in the fourth quarter. And basically, knowing this, I can now go ahead and apply my calendar studies. But as I said in earlier slides, you have to keep those secrets to yourselves, because if you publish them, then everyone's going to trade, and of course the usefulness of this discovery will be diminished or indeed eliminated. Okay, now let's look at those famous violations of regression assumptions. And of course, first, let's remind ourselves of the actual assumption that we are going to be violating. So we said that we want homoskedastic error terms, in other words, error term that has constant variance. And if you violate that, you get heteroskedasticity. Secondly, we want error terms that are not correlated with each other. We want serially uncorrelated and independent errors. If we violate that, we get serial correlation, also known as autocorrelation. And thirdly, in multiple regression, we don't want high correlation among the independent variables. Basically, we want independent variables that do exactly what it says on the tin. They're independent of each other. So if we violate that, we get multicollinearity. So for these violations, we need to do four things. Okay, define it, which we just did, by the way. And take that off. Explain their effects. So how does it actually affect standard errors, t-statistics, and so on? Detect them, so learn maybe the name of a test that you could perform. And finally, correct it or learn the name of a person who's come up with a solution. So it's maybe you can think of this as, rather than you trying to derive formula or even memorize formula, try in terms of memorizing names of models or people who solve those problems. So, starting with heteroskedasticity arises when error term variance is non-constant. So variance of error is non-constant. There are two types. The first one is known as unconditional. The reason why it's unconditional is because the variance of the error is not constant. However, it is not dependent or conditional on the value of x. So basically, while this could be technically, if you go by the letter of the law, you could say this is a violation of regressional assumptions. However, it doesn't in practice cause any major problems to the CFA player. So as a result of that, we can kind of ignore that. The second one is a little bit more problematic, type 2. This is your conditional heteroskedasticity. This is when the variance is not constant, however, it is also related to the value of the independent variable. In fact, next slide will show you what I mean in a picture, so I'll come back to this slide, but let's have a look at the actual problem. So the problem is that, notice on the horizontal we've got the independent variable, so at low values of x, notice how the variance of the error is relatively low, so the observations are closely clustered around the regression line. At high values of x, so as x increases, this variance expands. So we've got the dots scattered widely around the regression line. So we don't have constant variance, that is a problem, but also that non-constant variance is somewhat conditional on the value of x, even bigger problem. So this is what we call conditional heteroskedasticity, and this is one of the ways in which we can spot it. This is essentially called a scatter plot. That's one way to detect it. So if you come back here, let's now see what the effects are on our regression. So we know it is a problem. Now what happens to your t-stats? First of all, the b hat, the estimated value of the slope, does not tend to be impacted, which you might think is great news, right? So my betas are not affected. Great, so I can use them, right? The problem is that the standard error of the slopes typically tend to be too small, deflated. And if your standard error is too small, you take the number that's not affected, the b hat, you divide it by a lower denominator. Of course, anyone can tell you the t-stat will be inflated. And here is where the problem lies. If you've got a high inflated, artificially high value of t, then of course it means that you will be more often than not prompted to reject your null hypothesis, right? High t-stats result in you rejecting the null. And what's worse, you might reject that null even when the null, the original null, was actually true. You simply reject it because of the very artificially high t-value. Well, let's remind ourselves of what the null was. H0 says B1 is equal to 0. My slope is equal to 0. Say that was actually true, right? So in other words, say I did not have exposure to small cap stocks. But because of the artificially high t-value, I will have to reject that and say, oh, actually I have exposure to small caps. And the problem is the conditional heteroskedasticity. That, by the way, in statistical lingo is referred to as type 1 error. Rejecting the null hypothesis when the null hypothesis was actually true. And so here's one way to think of it. You can think of it as this gives you a sense of false significance. If you've got conditional heteroskedasticity present in your data, your slopes may look falsely significant when in fact they are not. Okay, we talked about the scatter plot being one way to detect this. Now let's look at a more formal way of doing so. The more formal way of doing so comes in the form of pretty much a name-dropping exercise, because I'm not expecting this to be a huge mathematical challenge on exam day, but you need to know the name of the test, and this is the Breusch-Pagan test. The Breusch-Pagan test. Now, I would say know vaguely what the test is doing, right? So we're going to regress the squared residuals against x. So notice this is not your underlying regression where you regress y against x. You're regressing the squared residual from the underlying regression against the value of x. Now, what is this going to do? What you need to compute here is the r squared, so the explanatory power of this regression. And now normally what we said earlier is that we want our r squareds to be high. That means that our regressions work. But look what you're regressing here. You're regressing noise against x. By definition, you want noise, you want errors to be random. So by definition, you would expect r squared to be 0. That will be your null hypothesis. That will be your null hypothesis. So if x does not explain the error term, that will be indication that we do not have conditional heteroskedasticity. So in other words, failing to reject the null of this test would indicate that we don't have problems in our regression. Now the alternative will be that r squared is greater than 0. Now remember, r squared cannot be negative, so it will be greater than 0. And this would basically mean, if it's significantly greater than 0, it would mean that you suspect conditional heteroskedasticity. Now, of course, how high is a high r squared value? We may remember that squared random variables may follow the chi-squared distribution. So this is a chi-squared test, whereby you'll have to compare the computed r squared value against the critical chi-squared value. If the computed value exceeds the critical value, then we'll have to reject the null and conclude that the alternative must be true. So that is your Breusch-Pagan test, and this is the kind of big picture understanding I want you guys to have for exam day. Now, okay, we're now moving on to the correction. How do you correct heteroskedasticity? The first method is to use robust standard errors. They are also known as white-corrected standard errors. The reason is very simple for that. In 1980, Professor White wrote a paper saying, explaining really with some mysterious calculus how we can fix these standard errors. Now remember, the standard errors that arose in conditional heteroskedasticity were too low. So what White essentially does to them, without going into the calculus, is White basically inflates them. White basically inflates them. So we get b hat over s. We inflate the standard error back to its value in the absence of conditional heteroskedasticity. That then reduces the value of t, and it essentially reduces the chance of making a type 1 error. It reduces that problem of your slopes appearing potentially falsely significant. So that is one way in which you can tackle heteroskedasticity. The second method, which is kind of unrelated, is to use a different kind of regression model. Now, the regression model we're studying currently is known as OLS regression. It's the idea of ordinary least squares. It's the idea that we try to minimize the sum of squared errors when drawing the line of best fit. Basically, we're not going to use exactly that model. We're going to use a slightly different model called generalized least squares, which modifies the original equation in order to tackle the heteroskedastic error term. Okay, done and dusted as far as the first violation is concerned. Two more to go. So, serial correlation, or also known as autocorrelation. Now, here you've got a couple of problems, potentially a couple of problems. There's positive serial autocorrelation, which basically says that a positive error today increases the chance of a positive error tomorrow. Negative error today increases the chance of a negative error tomorrow. So that is an example of positive autocorrelation. And then you got negative autocorrelation, which is exactly the opposite. Positive error today increases the chance of negative error tomorrow. Now, good news for you guys. In financial data, and of course as CFA analyst you should care about financial data, it is rare to see negative autocorrelation, so the more relevant to our case is the positive scenario, the positive autocorrelation scenario. So I want to start maybe by giving you a picture of what this might look like. So let's take a good old Apple example. Apple dollar sales. Over time, okay, and let's say 2007 onwards, obviously they launched pretty successful products. Let's see what dollar sales might have looked like. Okay, they might have been exponential for all we know. Now, of course, we are applying simple linear regression. We may also apply multiple regression, but for the sake of argument, I'm plotting here the sales over time, and I'm just trying to use a linear regression, put it this way. I'm trying to use a linear regression to predict this sales. Well, now I'm going to see a problem there, won't I? I'm going to see a problem, because how am I going to model an exponential curve using a straight line? And what I'm going to discover is that here I've got a lot of negative errors. So in the early years before the crossover point, my model would tend to overestimate the dollar sales of my company. So lots of negative errors here. A negative error followed by another negative error followed by yet another negative error. In the later years, after the crossover point, I've got a lot of positive errors, right? So a positive error here triggers more positive errors. And this is an example of positive serial correlation. Okay, common in financial data, especially when we look at exponentially growing variables. So let's see what the effects are on our regression. Well, again, yet another good news for you guys. You don't have to memorize a new conclusion, because typically positive serial correlation results in the exact same effect as conditional heteroskedasticity. In other words, our slope is unaffected, our standard errors are too low, and therefore our t-statistics are inflated. If our t-statistics are inflated, we tend to reject the null too often, and that leads to our famous type 1 errors, potentially rejecting a true null hypothesis. Remember, our null was B1 equals 0. If you falsely reject that, then your independent variable will look falsely significant, when in fact it probably isn't. How do we exit serial correlation? The first thing was the scatter plot that I draw. The second way involves a test, the Durbin-Watson statistic. Now this one is kind of more hands-on test, because you could possibly be able to interpret this on a scatter plot. So we will dive into a little bit more detail on the Durbin-Watson test. Now, firstly, what we look at is this idea that the Durbin-Watson test has an approximate value of 2 times 1 minus the autocorrelation in the error term. So let's take that equation and see what happens. So remember, Durbin-Watson is approximately 2, 1 minus r. Now, suppose I had perfect linear correlation within my error term. So r was equal to 1. I would get 2, 1 minus 1 equals 0. So the lowest value of my Durbin-Watson line, Durbin-Watson spectrum, is 0, and that will be indicative of very strong positive serial correlation. On the other end of the spectrum would be perfect negative correlation in your error terms. So 2, 1 minus 1 will actually give me the magic number 4. And 4 will be indicative of perfect negative correlation, very strong negative. Bang in the middle, we will have 2, 1 minus 0, 0 autocorrelation in the error term will give me the magic number 2. Okay, so that's 2. Right, and okay, like happy face. Obviously no serial correlation, nothing to do, so you're quite happy. These are the 3 endpoints. 0 is positive, 4 is negative, 2 no problems, no serial correlation. But again, the issue is, well, it's not so perfect. What if my value is 1.5? So here comes the Durbin-Watson critical table, which by the way depends on number of independents and sample size. So Durbin-Watson won't use degrees of freedom, it'll use the actual sample size. So based on the Durbin-Watson table, you'll come up with Durbin lower and Durbin upper. These values are always less than 2, but then you yourselves will have to compute the values to the right of 2. So the first one will be 4 minus Durbin upper, the second one will be 4 minus Durbin lower. At which point we can now have various territories where various things are happening. So as you may imagine, in the area that's closest to 2, we continue to apply our happy robotic face because we are close to 2 and we've got no serial correlation. In the area close to 0, i.e. this area here, we've got positive serial correlation. So key point is below Durbin lower, you're going to have positive serial correlation. And in this symmetric area to the right, we will have the negative, right? Positive, negative serial correlation. So above 4 minus DL, we've got negative serial correlation. And that, of course, leaves 2 areas unaccounted for. We'll put question marks there because in this territory, if your computed Durbin-Watson falls in those territories, we are going to essentially leave it as ambiguous or inconclusive. So there won't be enough evidence to sway us either way. But right, to cut a long story short, what is the key point that we need to learn? Remember, for CFA analysis of financial data, positive serial correlation matters. Positive serial correlation matters. So, what you can say is that if Durbin-Watson computed Durbin-Watson value is less than the Durbin lower, then this is indicative of positive serial correlation. That is, I think, the key point to take away from this. Okay, so underline that. That is your key point. Computed Durbin, maybe here, falling below the Durbin lower, indicates positive serial correlation, which is very common in financial data. Okay, so this slide pretty much tells you things along these lines. You will have to come up with the pair of criticals from the Durbin-Watson table. And again, that is a variation of what I drew. You will have 0, which is the perfect positive. You'll have the Durbin lower and the Durbin upper. And remember, above Durbin upper, if you imagine number 2 is here, above Durbin upper, we do not reject the null. Of course, null is that we do not have serial correlation. Below Durbin lower and Durbin upper, the test is inconclusive, and below Durbin lower, we conclude positive serial correlation. We talked about all that. Here's a concrete example. Durbin-Watson is 1.1 in regression with 5 independents, so k is equal to 5, and 40 observations, n is equal to 40. Now, if you guys have your Durbin-Watsons with you at the back of the Schweizer, take a few seconds now, open your books at the end, and look for those values. You'll have to go to the right, find the 5th column, which represents the number of independent variables equal to 5, then go down to the 40th level, which is the sample size 40, and hopefully you will find the pair of critical Durbin values as 1.23, 1.79. Now, because our computed value is 1.1, that is actually below the Durbin lower, which was the key thing I asked you to learn. When you're below the Durbin lower, that is indicative of positive serial correlation, so we're going to want to reject our null hypothesis of the happy robotic phase. Now, what is the preferred solution to this? Okay. Now, remember how we solved heteroskedasticity. Professor White in 1980 solved that, right? So we had to learn a name. White corrected standard errors. Well, here's another guy, Hansen. So learn this name. So basically, if you've got serial correlation, you're going to use the so-called Hansen method, which essentially, again, will take those deflated standard errors and blow some air into them. So again, if I've got the t, which is b hat over s, if I increase the standard error, I will limit the problem of inflated t statistics, and therefore I'll limit the type 1 errors that I'm getting. I'm going to limit that idea of false significance of my slopes. Also, as a nice trivia fact, Hansen also solves for conditional heteroskedasticity. So, potentially, if you've got both problems in a regression, you may suggest the Hansen method as a method that solves all your problems. And last of 3, we're going to look at Maury collinearity. Now remember, Maury collinearity occurs where 2 or more independents are highly correlated with each other. Now interestingly, this does exactly the opposite to what we were learning just now. So conditional heteroskedasticity and serial correlation deflated standard errors, inflated distance. This does exactly the opposite. So this time, your standard errors are inflated to start with, and therefore your t-stats are deflated to start with. Now if you've got lower t-stats, that means that more frequently than not you'll fail to reject the null. Now remember what the null was. This was your null. You'll fail to reject that. So more often than not you would be tempted to think your slopes are insignificant, when in fact they may be significant, but because of Maury collinearity, they appear not to be. So this kind of thing increases the chance of type 2 errors. You may remember type 2 error is when you incorrectly fail to reject a null hypothesis that was actually false and should have been rejected. All right? So the t-stats are artificially small. How do we detect Maury collinearity? Well, here we don't have Breusch-Pagans or Durbin-Watsons. Here we simply look at telltale signs. Okay, so there's not a test that we need to learn per se. Certainly nobody's name. What we need to do is we need to look at the f-stat. You may remember the f-stat was the overall validity of the model. If you prefer, you can also look at the r-square, which is a goodness of fit, or the explanatory power of the model, and then compare that to the individual t-statistics of the slopes. Now, normally, in a healthy, well-working regression, what we want to do is high f, high r-squared, and at least one of the t's being also high and significant. But when multicollinearity is present, what often could happen is you can have high f and high r squared, whereas at the same time, individually, all t stats are low, are below the magic number 2. All t stats are insignificant. And that is a logical contradiction, because the definition of f is that at least high f indicates that at least one t has to also be high and significant. So it is pretty much not possible to have high f at the same time low t statistics unless that's being caused by multicollinearity. So the way you can think of it is that individually the slopes may not be doing a good job, but because of the very high correlation, together they seem to be a driver of the regression. So this is something you can pick up easily by scanning the data output from your regression package. Remember, the ANOVA table will help me with the f-stat, and then I can look at my t-stats as well and draw those conclusions. The second telltale sign looks at the correlation, the pair correlation between the x variables. So the correlation between x1 and x2. If I say, okay, the absolute value of this correlation is greater than spot 7, because I know correlation cannot be a number greater than 1, so spot 7 probably is a candidate for a fairly high correlation between two variables. So if I see something like that, I'll probably say, you know what, I think I've got multicollinearity going on in this regression. Now, there is a downside to this method, and here it is. This sort of logic only applies to regressions with two independent variables. So please make sure you do not use this method if you've got 3 or more independent variables. And finally, of course, we want a correction, right? So heteroskedasticity we saw with White, serial correlation we saw with Hansen. How do we solve multicollinearity? Again, no more names. What we need to learn here that essentially if you've identified two variables that are highly correlated, say interest rates and inflation, highly negatively correlated, and they're causing multicollinearity, inflated standard errors, low t-stats, type 2 errors, etc., etc. Well, how do you solve that? Kick one of them out of the regression. Keep the other one, right? Keep one and kick the offender. It is beyond this particular reading to understand exactly which one we have to kick out, but we can certainly apply statistical procedures to understand what will give us the biggest bang for the buck. So, summing it up, that's a nice little summary of what we saw in the past minutes. We have 3 violations. We got heteroskedasticity, serial correlation, and multicollinearity. So, what is each one of them? Conditional heteroskedasticity was non-constant variance of error dependent on the value of x. It caused type 1 errors, which was the idea that we would potentially reject a true or null. And this would occur because the standard errors were too low and the t-stats were too high. We detected this with the Breusch-Pagan test, which was a chi-squared test, testing the coefficient of determination when regressing squared residuals against the value of x. And finally, we solved the problem with White-corrected standard errors, or robust standard errors, if you prefer. Serial correlation was the idea that errors were not random, but serially correlated. In financial data, the most common situation was that of positive serial correlation, which happened to cause exactly the same issues as heteroskedasticity, in other words, type 1 errors. We detected this with the Durbin-Watson test, and we solved for it via the Hansen method. Finally, Maury collinearity looked at two or more variables that were highly correlated. That actually caused type 2 errors because standard errors were inflated due to Maury collinearity. Whilst there was no formal test to detect Maury collinearity, we could still look at a conflict between the overall validity of the test, which is proxied by the F-test, and the individual significances of the slopes, which is looking at your individual T statistics. We could also detect Maury collinearity by looking at high correlation among the independents, but that only worked if the independents were equal to 2. And of course, the solution to Maury collinearity was to drop one of the offenders. Okay, moving on to model specification issues. First of all, we need to think about the selection of our explanatory variables. We need to be careful not to omit important explanatory variables. We need to potentially think about the correct transformation of these variables, and we shall see examples. Because if we fail to specify our models correctly, that of course will affect the reliability of our slope coefficients, T statistics, conclusions from our hypothesis tests. Right, so here are different examples of misspecifications we may face. Functional form misspecifications. So this is where important variables are omitted. So you forget to, or either forget or you fail to identify a relevant explanatory variable. Secondly, we may not transform a variable correctly. The most common occurrence of that is when we've got a variable that exhibits exponential growth. Normally the way we transform these variables is by taking the natural logarithm of the variable. We shall see an example of that in a minute. And thirdly, data may be pulled improperly. So if you're talking about the real estate market, before the credit crisis and after the credit crisis, they're different sort of animals. So if you pull them together, you may be pulling your data improperly. And the second category of misspecifications are time series misspecifications, and this is where you basically get your timing perhaps wrong, or your time series wrong. So X becomes a lagged Y variable with serial correlation present. Now what that basically means is that you're trying to model Y at time t, for example, by looking at an intercept, a slope, and Y, the same value at a previous period. So in other words, for example, I want to model my sales next month by looking at my sales this month. Now, in another reading, we will define this type of model as an autoregressive model. But make no mistake, these models will be misspecified if there is serial correlation present in your error terms. So in terms of actually misspecification, you cannot run an autoregressive model with serial correlation in it. Secondly, we're not allowed to forecast the past. We're not allowed to forecast the past. Yeah, that's quite an obvious statement, isn't it, guys? So, for example, I may take a variable on the 31st of December 2014, 31st of December 2014, which is essentially the end of year, and then use that data point, use that variable on that date to actually forecast the performance of my company during 2014. Of course, that won't make sense because to predict 2014, you won't know the final value of the variable at the end of the year. And thirdly, we may have a measurement error in the way we specify our variables. This normally occurs in qualitative variables where we need to use proxies. We shall see an example of that. So, what are the effects of this model misspecification? If you misspecify your model, you basically are going to bias your regression coefficients, and ultimately this will lead to inaccurate predictions and unreliable testing. Now, let's look at a concrete example here. This example is based on a study performed by Wang and Xu in 2004. Please remember not to memorize the actual specifics of the study. Use it as an illustration of the model misspec issues. So what they try to predict is Chinese portfolio stock returns in the period July 96 to June 2002. And they use the following explanatory variables. They use portfolio beta. They use the natural logarithm of market capitalization, the natural logarithm of the PB ratio, and free float. So here's your regression equation. Now, misverification number 1, omitting an important variable. So basically, if Wang and Xu forget to include the natural logarithm of the market cap, assuming that that was actually a relevant variable, that of course will bias our regression. Misspecification number 2, failing to transform a variable. Now, market capitalization tends to exhibit exponential growth. So as a result, we tend to transform that by taking the natural logarithm of the variable. Misspecification number 3, incorrectly pooling the data. Now you gotta think, is 96 to 99 different or the same in nature to 2002? If they're very different periods, perhaps you should run 2 separate regressions. Misspecification number 4, use lagged Y variable. So for example, we could use the previous month's return as an independent variable. As I said earlier, this is exactly what we're going to be doing in auto regression, but we cannot do it if we've got serial correlation present in the time series. Misspecification number 5, forecasting the past. The example here is using end of month market cap instead of beginning of month. So I'm using end of month market cap to actually forecast the return of that portfolio at the end of the month. Doesn't make sense because that data point won't be available at the beginning of the month. Misspecification number 6, measure X with error. So this happens because what Wang and Xu really wanted to incorporate here is the quality of corporate governance. But of course, this is a very abstract, very qualitative variable. You can't just measure corporate governance easily. So you need to use a proxy for that. The proxy they used is free float. And that's all fine. The problem is free float measures other things as well. It's only a proxy. So it will measure the quality of corporate governance with an element of error to it. Okay, now moving on to qualitative dependent variables. Now, earlier in our studies, we saw a qualitative independent variable, which was called a dummy or binary variable. So that's when X was qualitative, when X was binary. Now we've got a situation where Y is binary. So Y can take the values of 1 or 0. So in other words, the output from the regression essentially boils down to yes versus no. And the most common scenario here is maybe when we want to forecast whether a bond is likely to default. And we want basically a binary answer, yes or no. So the qualitative dependent variable could take the value of 1, which would mean default, or the value of 0, which would mean survival. Okay. Now the point we're trying to make with this is we cannot use the good old OLS regression when we are doing this. Okay? When you've got a qualitative dependent variable, you can't just do the OLS regression. So what are we going to do instead? Okay, we essentially have 3 available models to yourselves. The first model is known as the probit model. Okay, so the probit model estimates a probability of default, i.e. a PD, a probability of default given values of X based on the normal distribution. So yeah, probit models will estimate a probability, but because they're based on the normal distribution, they kind of assume the world is normally distributed, which may or probably may not be true. Similarly, logit models estimate the probability of default based on the logistic distribution. Now, you may not have come across the logistic distribution before, but all you gotta know about it really is that it's computationally easier than normal distribution. So if computation power was an issue, you would go for a logit model. And finally, we've got discriminant models. Now, what discriminant models do, instead of they basically computing a probability of default, what they'll do is they'll produce a score or a ranking. So what you want to think about here is basically your credit score. If you want a credit card or a mortgage, your lender is more than likely to check your credit score. And when they do, they're basically relying on what's known as a discriminant model. So this discriminant model, based on a variety of variables such as the number of credit cards you got, the timeliness of your payments, the amount of unused credit you've got, etc., will produce a score, let's say between 0 and 999, and then based on experience, your lenders will put you in various buckets. So you may be put in a bucket called prime. In other words, all lenders would be willing to lend you, and so on and so forth. So each bucket has an associated likelihood of default. Now, let's talk about economic significance versus statistical significance. Now, remember, a lot of these things we're talking about here are looking at statistical significance. Is the slope statistically significant than 0? Is the X stat high? Is the R squared high? These are looking at really the statistical power of your regression, not necessarily at how well it fares in the real world. So the analyst must carefully analyze two things. First of all, how well the statistical analysis actually does its job. Have we violated any assumptions? Heteroskedasticity, Maureyka linearity, serial correlations were all problems, all violations of statistical assumptions. Also, have we misspecified the models? Have we omitted an important variable? Have we failed to transform a variable? Have we, for example, used a variable as a proxy and therefore measured something with error, etc., etc.? So these are all model misspecs. And ultimately, once the analyst is satisfied that the statistics work out fine, then the big question, is this model really gonna survive the test of the real world? Because remember, it's all well and good in terms of statistics, but in the real world, we pay commissions, we pay taxes, and we can go bankrupt. So there is risk in those strategies. So once we take those things into account, does the strategy still produce returns which are meaningful? Right? So think about those things. Okay, guys, we are nearing the end of this fairly lengthy reading, so well done to yourselves for being with us so focused for the entire reading. What have we covered? Well, we again, as usual, went through several hypothesis tests, much like simple regression would have done. We, of course, predicted the value of the dependent variable given this time more than one independent variable. We continued working with your ANOVA tables, so analysis of variance tables, and therefore we again were able to compute things like R squared, adjusted R squared, standard error of the estimate, F stat, which was the overall importance of your model, overall validity of your model. And essentially, at the end, we also looked at problems and issues of model misspecification. So this is quite an important reading. There are a lot of things that really require you to look at a conceptual understanding. So, for example, when we look at the violations, did you understand what the violations were doing? Did you understand what the effects were? How to check for them, how to correct them? There's very little in the way of actual computation. So it's about you understanding, guys. So I hope you had a good time. I certainly did. and I hope to see you for another wonderful reading. All the best and have a good time studying. Goodbye.